Very good morning, everyone. I'm happy to attend and talk about a part of my research in understanding how the nanomaterials that are used in food and agriculture are contributing to the totality of exposure. Before I start with my presentation today, I would like to thank the organizers for inviting me, especially Professor Lou Ho for inviting me and introducing me to this institute here, and Wendy and Fiona for making all these arrangements for the presentation. So without much delay, let me directly go to my presentation. Before I start my presentation with my subject, I would like to introduce my lab, focusing mostly on understanding the interactions of nanomaterials with biological system, with a particular interest in understanding their safety to consumers when we take in nanomaterials through oral route, what happens and how do they have any implications for our health, and also working on developing exciting applications of nanotechnology for solving daunting issues related to food safety and food security. And a minor part of it is also to work with industry, enabling them to make their product better through nanotechnology applications. So and then I will directly start with my presentation, which is on the nanomaterials and their role in dietary exposure. But first, I will introduce what nanotechnology is. By definition, it is the applications of or manipulations of matter in nanoscale to generate size-dependent functionalities different from atom molecules of bulk materials. I thought I will start with this simple definition here, because if people are not really aware about what nanotechnology is, totally unaware about it, it will be difficult to comprehend what is their role in manipulating the toxicants or contaminants that are entering through food. So when we reduce the size of materials in nanoscale, what we see is they occurring novel properties in terms of their physical as well as chemical properties. So we mostly are aware or are familiar with entities, whether in molecular or atomic entities or in their bulk counterpart or bigger forms. Take gold, for example. We mostly are familiar with how gold atom will behave, or we also know how a gold coin or a block of coin will behave. But what we know is there is a state in between the atom when it come together to form a crystal to form bulk counterpart. There is a state called nanomaterial, and that's where the dimensions are in the nano size, which is 10 to the power of 99 meter. So when they are in that size range, they have unique properties, and that's because they have an extremely high surface area for a volume of matter, and they have most of their atoms that are exposed to the outside, or they're actually presented on the surface, as you can see here. And as a result, they may have surface properties like sometimes extremely smooth surface, or maybe even cracks sometimes, so it can be depending upon the material. And then there is another important aspect, is the dominance of quantum effect. Because most of the properties of bulk material, as we know, they are according to the laws of motion or Newtonian physics, or the way they interact with other matter or each other. But the atoms or molecules are obeying the laws of quantum physics. But when you got this intermediate entity in the nano size range, they do have an in-between state. And sometimes there can be the quantum effect taking over on this particle. And as a result of all these, we have wonderful novel properties. And that was the excitement about nanotechnology. And our interest was in making the materials stabilized at this nano range so as to get these properties more permanent. Now we do have the technologies and know-how to make nanomaterials out of many diverse materials, including metal oxides, aluminum oxide, zinc oxide, or even silver. All these are, we can make nanomaterials. Even from proteins, you can actually make proteins to fold or to aggregate together to form nano cages, or even materials like clay, for example, ceramic materials. So it's a diverse range of materials can be put into this nano range. Now we know most of these to know how to generate that and stabilize this. As a result, we can enjoy the novel properties that are provided by nanomaterials. And these novel properties, especially their biological interactions, they are different from the bulk counterpart, are applied in diverse sectors, including food and agriculture. And if you look into the agriculture and food, you can see their application right from the beginning of the food supply chain, from the production stage to improve nutrition, to ward off the unwanted infections, or to introduce vaccine or growth hormones, etc., to animals or even to plants, so as to generate a higher yielding or obtain more productivity from those farms, for example, all the way to enhancing the flavor perception, the texture of the food that we consume by adding directly into the food matrix that we eat, for example, silicon dioxide, titanium dioxide, etc., and also into sensing and tracking applications. So there are diverse set of applications, so as to understand that the industry for nano application in agriculture and food combined together can be almost $1 trillion business. And obviously, as a result of that, if we are using that much of nanomaterials in agriculture and food, there is a highly likely chance that they will show up in our plate. And of course, they do. And this is how, if you are scanning the market for products that incorporate nanomaterials, will look like. There is a survey study that we did in Singapore, just going through the by labeling itself to find out which are the material or food products that uses nanomaterials, and you can see a lot of chocolate-based or candies, as well as milk. Um, Dairy products using nanotechnology or nanomaterials in them, and newer applications of food processing surfaces using nanotechnology. And if you look into what type of nanomaterials are used, you will see silicon dioxide as the most prominent or frequent one encountered, followed by titanium dioxide, followed by nanocalcium or microcrystalline cellulose, nano silver in food packaging, etc., etc. And these are some of the applications. And as a result, we consume a lot of these materials. Now the question is, what is their effect, especially these ENMs referring to engineered nanomaterials? What is their effect on the totality of the exposure to chemicals? As we know, when a human being is placed in the matrix that we always deal with, whether it is an outdoor environment or indoor environment, we are constantly exchanging chemicals to our body and from our body. And the exposome is a concept that talks about the totality of the exposure from all exogenous endogenous sources in the internal chemical environment. In the internal context here is the body, and that the chemicals that we will be exposed in our lifetime from our endogenous as well as exogenous from the environment. And that can of course happen through the air that we breathe in, which contains a lot of chemicals and gaseous molecules which may not be really good for our health, involving water that we drink, which contain, nowadays we know, we hear about microplastics, engineered nanomaterials, EMA, and other plastic related chemicals. And in food, again, there's a lot of chemicals that we are constantly being taken in, and then through the cosmetics that we apply. So all these are entering our human body. Now the question is about this engineered nanomaterial from food. What is their role in shaping or in influencing the toxicity of these contaminants? And that's an interesting concept. So I will start with the intrinsic property of nanomaterial. Most of my research previously studied it, and even now, we are trying to understand what is the physical and chemical properties of nanomaterial that prove itself to intrinsic property that may have an effect, or that may have an adverse health effect or toxicity. As a result, we have identified when a nanomaterial, that is the size range of nanoscale, come in contact with a biological interface in here, denoted with this lipid membrane, you can see there are different aspects of nanomaterial that could prove to be toxic or adverse effect. For example, their redox chemistry giving rise to the formation of free radicals, which can cause oxidative stress, or their surface chemistry giving rise to formation of cationic surfaces, giving rise to membrane damage, or the imperfections or crystal defect in certain nanomaterials, especially crystalline materials like silver, for example, giving rise to dangling bonds and then free radicals or membrane damage. And then their dissolution to release heavy metals, because this material with which it is made up of, for example, silver can shed silver ions which are toxic, zinc oxide can shed zinc ions which are toxic, for example. And then there is the aspect ratio. If they are like elongated like a asbestos, for example, they can generate a phenomenon called as persistent fibers in the body. As a result, can give rise to reactions, biological reactions similar to cancer formation, etc. So we have identified these intrinsically because they are nano, and then because they have some certain sizes as well as their surface chemistry, they can be toxic. So that the lesson is they have intrinsic property to be toxic. Now, when you talk about a nanosystem, a nanomaterial is not a single entity. Sometimes it may be made up of different components, as in the case of quantum dots that are used in display device. This was an exciting project that we recently take up to understand how that complex materials that are embedded, or the components that are used in making a functional complete quantum dot, contribute to its toxicity. If you look at the structure of quantum dot, you know this is a core structure made up of cadmium selenide. Cadmium is toxic, it's a heavy metal. And now most often that cadmium selenide core is covered with a shell called zinc sulfide usually. And then on top of that, you will have many of those polymers which are helping the dispersal of this quantum dot into a matrix, for example, in the TV panel. So we actually generated these kind of complete quantum dot and their intermediate for study. And this quantum dot is the same as a patented quantum dot that is used in our display devices. And then we tested for its toxicity to cells. We wanted to see each component, how it actually contributes. And as a result, you can see the complete quantum dot is, in comparison to its components, is more toxic. It is not so we compare their effect or the contribution of each of component. Usually, each of the component, they can actually have three different type of interaction. Either it can act upon another component to reduce the toxicity, or it can add on to the toxicity of another component to increase an additive effect, or it can give a synergistic effect, which means a magnification of the toxic effect. So there is a mathematical tool that we can devise to understand it, and obviously you can see for the complete quantum dot, we see a combination index which is far less than 1, which means it's a synergistic effect, it's not even an effect. But putting a shell on the core is a adverse, or is an opposite effect. It will reduce the toxicity of cadmium. And then we understood why this complete quantum dot is more toxic is because it has this polymer, which is cationic polymer, which enhances the uptake of this quantum dot component into the cells, and then it dissolves the shell and the core structure to generate and release the cadmium, the most toxic one, into the cytosol to generate a toxic effect. What we understand from here is, in a nanomaterial, when there are multiple components present, although the core particle is the toxic one, the toxicity is even higher than the core particle, because the surface molecules actually enable its uptake into the biological system like a cell, and it enhances the toxicity. So it's not a simple additive or a different effect. Now, another example, what we are looking at is the property of processing dependent change in the toxicity. When we consider a toxicant, for example, usually when a toxicant is taken, it is toxic. we know that it will, it may not change, or it may have a constant kind of a toxicity as and when it goes through different biological environment. Now, when it comes to the nanoparticle, it is different. That's what the study that we recently concluded shows. Again, using quantum dot as a model nanomaterial for its simplicity and its possibility to look into that aspect, we use that as a model. What we did is we subjected this quantum dot, the same quantum dot, complete quantum dot we studied earlier, into different chambers as it will go through in a gastrointestinal tract, to saliva, to the stomach, to the intestine. And what we looked at it is a change in properties in terms of its physicochemical properties, whether it is a size changing, whether the surface chemistry is changing. We track that, and then we actually check for its toxicity using the same multi-parametric analysis that we develop in our lab. And when we look into that, when it goes to the first stage, which is the saliva, actually the toxicity reduces in comparison to a pristine particle. So what we understand is saliva actually coats those particles, and it actually agglomerates the particle, and as a result, there is a reduction in the toxicity. But when it reaches the gastrointestinal, in the stomach, for example, actually the toxicity starts to increase, and that's because the acid in the digestive juice actually reduce. You take away the shell, and it dissolves, and you start to actually getting the new surface chemistry formation, and because of the proteins, and because there is this polymer is now removed, and it is now decorated with the proteins, for example. And most interesting fact was when it reaches the intestinal stage, there are these gastrointestinal juices, as well as many of the other parameters that actually enhances the toxicity far higher than the pristine one from the starting point. And again, that's because the bile salt, for example, decorated the surface and facilitated the uptake of this material. So what it shows is the toxicity of nanomaterial is not static, it is dynamic, and it interacts with a different biological system differently. As a result, in our, as the study shows, it can get enhanced toxic effect. So that's one way it shapes the toxicity. Now, nanomaterial by itself is toxic sometimes, and it can also have other effects that we learned. But nanomaterials it can also serve as a vehicle for the transport of other chemicals. That's most interesting. So we know that when you put a nanomaterial in a complex biological system, what will happen is molecules will start to adhere to the surface and accumulate. And now what happens is this entire system acts as a vehicle, a transport mean to actually take these chemicals or molecules which otherwise will not get into the cell. Because now nanoparticle enter the cell through a different mechanism, it can facilitate the uptake. Here is an example showing a nanomaterial that is interacted with milk. This study is published in nanoscale. What we saw is when you interact the particles with milk, for example, certain type of proteins can be enriched on the surface because their affinity for the nano surfaces is different, and we prove it using different analytical tools, including the use of high resolution imaging using the X-rays to show that how the different biomolecules interact on the surface of titanium dioxide here, as you can see. And it can also show that using LCMS for the protein, there are certain type of proteins are enriched. If the proteins are enriched, you may ask what is the problem, and we'll encounter that. I will come back to that point. But before that, I also want to show you that when the nanomaterials are there in the system, for example, when we study the epithelial cells, this is the epithelium that actually decorates the small intestine for the nutrient absorption. So we actually studied the nanoparticles, and our studies show that these nanoparticles can interact with the molecules, the protein molecule that hold together the cells. Those are called adhesion or epithelial junctions. And then we can see that the presence of nanomaterial will disrupt this protein assembly so as to create crevices or create those kind of cracks in between. Otherwise, should be a tightly sealed epithelial layer. And as a result, now you can imagine that when these nanomaterials, which are decorated with these chemicals, when they come, they get a free passage through this. We tested that hypothesis, and we found that nanomaterials can actually cause those kind of deformation of proteins, as we saw earlier. When the protein absorbs, it can change the structure and function. And as a result, if you're measuring the antigenicity, you will see the structure is altered. The antigenicity is increasing, antigenicity as well as allergenicity is increasing in comparison to a food matrix, that is, example, taking milk as an example. When it is interacted with the nanoparticles of titanium or silica, these are the most commonly used nanomaterial, we show that. And then there is an enhancement in the antigenicity as well as allergenicity that we tested using master cell line. And again, that is because of the structure change, but also there is another mechanism that we showed, is because it actually facilitates the uptake of allergen across the epithelial layer to reach master cell. This is a transfer assay that we have created for this specific purpose, and you can clearly again show that the allergenicity that is measured in terms of the degranulation of master cell is increased when you have the allergen presented along with the nanoparticle. So there are different, which otherwise the protein may not percolate or seepage through that epithelial layer. Now it is facilitated through the presence of nanomaterials. So these are some of these ways that nanomaterials will facilitate or shape the other chemicals or other allergens or potentially hazardous agents to exacerbate their effect on health system. So through primary particle property, that we show that because of the core chemistry, because of the surface chemistry, they may have an effect. They can dissolve or disintegrate and give rise to chemical toxicants. The surface chemistry, hydrophobicity, etc., can actually facilitate uptake or create those kind of epithelial compromise the epithelial integrity, or and the surface, along with that surface absorption, can give rise to a free passage for the chemicals or toxicant across the epithelial layer, so as to make their availability to the biological system higher. So these are some of the ways that we have identified that the engineered nanomaterial present in the food can manipulate the exposome in dietary exposome. So with that, I would like to conclude my presentation, and I would be happy to take questions from you. But before, I would like to acknowledge contributions from each of my students who work tirelessly for making these exacting discoveries possible. So my collaborators and funding agencies, I would like to acknowledge them for their enabling these studies. Thank you.